Yeah, welcome everyone to the virtual market design seminar, and thanks a lot for participating. I'm happy to announce today's speaker, Stephan Lauermann from University of Bonn, who will present his project Auctions with Frictions. Yeah, thanks a lot for presenting today, Stephan. To remind everyone of the rules of our seminar, Stephan will make breaks throughout the talk, and if you have a question during the breaks, you can just unmute yourself and ask a question. Or if you would prefer that I read the question, you can also ask via chat. Yeah, that's it. And in a couple of minutes, I will post the slides via chat so you can have access to it. Yeah, Stephan, the floor is yours.
Thank you. Thank you very much. Thank you, everyone. I see so many faces. That's wonderful. So this is joint work with Usher, and we want to incorporate frictions into a model of auctions. So many of you are interested in auctions, so I hope you find this project interesting as well. So the basic setup is a setup of a private value auction. There is one seller who owns an indivisible object, and there are n buyers who have private values v1 to vn. So one reason to be interested in auction theory is because we can use auctions as a tool to study price competition in markets for assets or services. So think about someone who sells a house. He or she, may collect a few offers and then take the best. Or think about someone applying at banks for a loan, then she would apply at banks for loans and then take the offer with the best credit rate terms. Okay, so this is not a formal auction maybe, but it still captures, it has some features that it shares with an auction. So there's some form of price competition, there's a limited number of bidders, and there's private information on the side of the bidders. And so we may use auctions to, as a theory, to ask ourselves, how does price competition work? Is it efficient? How do markets deal with private information? Now, when looking at these sort of scenarios that I've gave here, you may notice that in many of these settings, there will be additional features, that are not in our standard conventional auction that I've shown up here. In particular, the recruitment and motivation of bidders might actually be a central issue. So in this conventional auction, there are n bidders and they're just waiting there, they're well known and they're ready to bid. However, when I'm selling a house, it may be difficult actually to identify bidders. I have to search for bidders, I have to motivate them. Second, there's the commitment ability of the auctioneer in these scenarios may often be limited. And last, the interaction between the seller and the bidders may be affected by information that the auctioneer himself or herself has or is trying to learn. So we may think of these features here as being frictions. And in our paper, we propose a model that captures some of these features. So in particular, in our model, the number of bidders n will not be exogenous, but we'll think about it as being endogenous and the outcome of a game. So more specifically, the main feature will be that n is endogenously determined jointly by the actions of the seller and the bidders. So specifically, the seller will exert costly effort into recruiting bidders and contacting bidders. And on the other side, the contacted bidders may or may not participate because participation will come at a cost. So there are costs of acquiring information to prepare a bid. So if I want to buy a house, it will be costly for me to learn about the house. How would it fit my family? What is the real value of the house? And so on. Okay. The main trade-off here from the viewpoint of the seller is that recruiting more bidders is a good thing. First, because it increases competition. So for any given value V, a bidder submits a higher bid if there are more other bidders around. And second, there's a higher probability of having a high value bidder. On the other hand, if more recruitment is anticipated by the bidders, it will be harder to motivate bidders to actually participate given their participation cost. Okay, so and these two can feed on each other. So it can be a vicious cycle between the seller recruiting more and more bidders and the bidders becoming harder and harder to motivate to participate. And the main finding is that this leads to inefficiencies So one inefficiency is that there can be wasteful recruitment by the seller. And
Well,
second, there could be a market breakdown, so we don't get any trade. Yeah.
hello, may I ask a question? Steinberg from the London School of Economics. Do the bidders know that there's the number of bidders? The bidders know how many other bidders there are.
So that will be an important point, yes.
Because you see, if I didn't know how many bidders there are, that's different than if I knew that there are many more. So
right. So in many of the settings that I just gave, you may be uncertain as a bidder at how many other bidders there are. So we'll think about that, and we'll think about the incentives of the seller. Exactly. Okay, so the main finding is this inefficiency. There may be wasteful recruitment going on because of this vicious circle, and there may be market breakdown, so actually no trade and unraveling of the market. Before getting to the models, I will talk about the literature later. The contribution here will be sort of in combining the recruitment effort of the seller, the entry cost of the bidders in a model with limited commitment. Good. So now to the model. So here's the basic. So I will give you a basic setup of one model of an auction in which the number of bidders is jointly determined by the seller and the bidders. Okay. And we'll think about that a little bit and then think about variations of this. So I'll tell you about the model now. At the end of this slide, there's bold questions. And I'll stop there. And usually, you know, there are a couple of questions at that point. So we'll discuss it and want to make sure that everyone is on the same page so that this model is understood. Okay, so here is the model. It has 3 stages. First, the seller decides how much effort to exert. Effort translates into a stochastic number of bidders. Number of bidders is Poisson distributed with a mean equal to the effort x. And effort x comes at a cost x times s. Then the contacted bidders decide whether to participate or not. And participation comes at a cost c. At the time that the bidders decide whether to participate or not, the bidders do not observe the recruitment effort x. Okay. Then those bidders who choose to participate, they learn the number of participants, little n, and their own private value v from a distribution g. And after they've learned little n and v, they submit their bids, the highest bidder wins, and the bid pays his or her bid. So then the game ends. Payoffs realize if the winning bid is equal to P, the seller's payoff is P minus X times S. X times S is the total recruitment effort. The winning bidder gets the value V minus the price minus the cost. The losers pay the participation cost minus C, and the non-participants have a payoff of 0. So it's better not to participate than to participate and lose, right? That will be the main consideration of the bidders. And I will study the symmetric perfect Bayesian equilibrium of this game. Right? Game has 3 stages, just to be sure. So first, seller chooses recruitment effort, then the bidders decide whether to enter, and then we have the bidding stage. The way we'll solve it is from the back. So we'll first solve for the bidding strategy of the bidders on the bidding stage. Then we'll go back, and given how they will bid on the bidding stage, we'll look at what are the incentives of the bidders to enter. This will give rise to the entry probability Q, and then we'll go back to the first stage, given how bidders behave in the auction and given their entry behavior, we'll look at what is the optimal recruitment choice by the seller. Okay, that's our game. And then after we've done all of this, we'll discuss a few variations. So variations we'll discuss, I think some, we had a question. So we'll look at, what happens with other auction formats. We'll look at settings in which buyers may be heterogeneous. Notice here, these bidders are homogeneous. At the time the bidder is called and asked, do you want to participate, yes or no? The bidder doesn't know anything. He has some expectation about the expected value, but doesn't have a private value. And all the bidders have the same entry costs. We can think about a variation in which the number of other bidders is not observable. So the little n here, this was the question, right? May be unobservable to the bidders in many scenarios. So we could compare what happens with observable numbers of participants and unobservable participants, and we'll see there are new consideration for the seller. In this model, the bidders do not get to observe the seller's recruitment effort X. So they don't get to observe how many other bidders are contacted. But in equilibrium, they will have a correct conjecture. So in equilibrium, it's known. Now, in many scenarios, there may be uncertainty by the bidders, and we may want to think that the bidders learn something about the seller's recruitment effort from the fact that they're contacted. That will have interesting effects. And also, in some of these scenarios that I gave you, there will be some interdependent value components, so adverse selection going on, and that will also be an interaction with what we've discussed here. So this will be another variation. And while I'm not going to study sort of the optimal design of an auction, I'm interested in an auction as a stand-in for studying price competition. We may still be interested in what are sort of the incentives here. So we want to maybe learn about what are the optimal fees for the seller. Maybe the seller wants to set a subsidy, optimal reserve prices, and so on. Okay. So now the promised bold question. So are there any questions?
Have you introduced limited commitment at this stage?
Okay, so limited doesn't, yes. So, so limited commitment would be in the unobservable recruitment effort. So this is sort of the main part. So the seller cannot commit to a particular recruitment effort choice, and you will see how this plays out.
Okay, thank you.
And in addition, here we're not looking at an optimal mechanism. So the optimal mechanism may involve entry fees or subsidies. Okay, so we're not looking at that for the time being. Okay, any further, is the model clear? So the seller first chooses a recruitment effort X that translates into a stochastic number of bidders with mean X. A higher expected number of contacted bidders comes at a higher cost. The contacted bidders don't know how many other bidders are contacted. They have to decide, do I want to participate or not, based on their equilibrium knowledge of how many other bidders get contacted, and based on their anticipation of how many other bidders will participate and how they will bid. And then the bidders participate here in a first price auction, and with observable participation for now.
Hello.
Yeah.
So I'm not entirely happy with seller chooses unobservable recruitment effort. If I'm a bidder,
yeah,
recruitment effort to me is a proxy for how many other bidders there'll be there. It's indirect, and maybe if you spending a lot, you're the seller, you have a lot of effort in getting bidders, then I think, well, I may have a lot of competition, and if you don't advertise very much, then probably there'd be fewer. But to me, the key thing would be, piece of information would be to get a general idea of how many bidders there were, not how much effort you put in to the auction as a seller. Is there any, I'm going ahead, but is there any modification where the bidders have some idea of how many other bidders there are? Because that's, to me, much more important than how much recruitment effort. In fact, the recruitment effort's more likely to be observable in the first place. It's just the number of bidders.
Okay, so I do not know. So many company, yeah. So you get a call. You don't know how many other people get a call, maybe, but you're sure there will be scenarios where this will be a little bit observable. More generally, the fact that I'm contacted might tell me something that many others have been contacted. So there's sort of a signal. But what you're asking about is the little n here. And so here I'm assuming that every bidder knows exactly how many other bidders there are at the bidding stage. And we could also think about a setting, and we will actually think about a setting where the participation little n is unobserved. So the bidders do not know how many other bidders they're competing against. Mm-hmm. And the seller may want to say, there are lots of other bidders you're competing against, so you have to submit a very competitive bid. But as a bidder, I may or may not believe that. Okay? So that will be an important variation, exactly. Is that your?
Okay.
Right.
Okay. Thank you.
Okay. So shall I continue? Great, thanks. Good, so we'll solve the game from the back. First, we'll solve for the bidding strategy on the auction stage. Then we'll look at the entry probability on the entry stage, and then we'll study the recruitment choice of the seller. Auction stage. And the auction stage, each participant learns the total number of participants, little n, and the own value. You can think about the bidders having to decide whether or not to travel to an auction site. And when they arrive at the auction site, they see in this variation how many other bidders there are, and they also observe sort of what the value of the object is to themselves. Then knowing n and little v, they will submit a bid. So this is basically just this symmetric first price auction, and the symmetric first price auction has a unique symmetric equilibrium that you find in Milgram or Krishna's textbooks. We can denote this equilibrium by beta FPA. What's important about this equilibrium is that bids will be below the value, so bidders are shading their bids. Second, if a bidder is the only bidder, the bidder will submit a monopoly price of 0. The bids are increasing in the number of other bidders, so this is reflecting competition. And as n becomes large, the bidders will behave competitively, so the bids converge to the true value. So in that sense, this is sort of the basic idea in which auctions reflect price competition with a limited number of sellers. Standard auction example here, the values are uniformly distributed between 0 and 1. In this case, beta FPA, if my own value is V, if the total number of bidders is n minus 1 over n times V, which has the properties I just described. So we've solved the auction stage. So now let's go back to the entry stage. So given a recruitment effort X and a participation probability Q, the expected number of participants is X times Q. So this is the participation level, and we'll denote it by lambda. And the number of actual participants is going to be also Poisson distributed with mean lambda. So this is one of the nice features of the Poisson distribution, that the number of contacted bidders is Poisson distributed and the number of actual participants is also Poisson distributed. So we'll talk a lot about lambda. So given lambda and given the behavior of the bidders in the auction states beta FBA, a bidder can calculate her expected utility from entry. We'll denote this by U of lambda. And natural implication of what we just had is that U of lambda is decreasing in lambda and U of lambda goes to 0 and as lambda becomes large. So if I expect there to be many other bidders, given that the entry cost C is strictly positive, a bidder will not want to participate. On the other side, if a bidder is the only bidder, he or she will want to participate, so we'll assume U of 0 is larger than C. So somewhere in the middle, there will be a break-even participation level lambda V max, at which a bidder is just indifferent between entering and not. And this lambda V max, that will determine the best response. Okay, so if lambda is smaller than lambda V max, the bidder will want to enter, so Q has to be equal to 1. If lambda is equal to lambda V max, the bidders are indifferent, and if lambda is larger than lambda V max, bidders will not want to enter, so lambda has to be equal to 0. Q has to be equal to 0. Okay, so the entry stage is characterized by the bidder's break-even participation level. So here is just a picture of U of lambda for the case with a uniform distribution. U of 0 is a half, of course. Then U of lambda is decreasing. One thing that we'll use is that U of 2 is equal to 0.15. So if the entry costs are 0.15, then the bidder's break-even level is at 2. Okay, and of course, if the entry costs are smaller, so if the entry cost is 0.04 in this case, the lambda V max will increase to 5. So the lower is the entry cost, the higher is lambda V max. So that's the entry stage. So we've solved the entry stage. Now let's go back to the recruitment stage, if there is no question. Good.
Sorry.
Yeah.
So is there an implicit assumption about restriction to symmetric strategies at the participation stage here, or is it?
No. So good to hear. So in the Poisson games, symmetry of the equilibrium is not a restriction. So basically, we have a large number of bidders, and from the viewpoint of each individual bidder, there's a distribution over what the other bidders are doing, and that's always going to give some rise to symmetry. Okay. We can talk about this later, but with the Poisson assumption, this is really without loss. And otherwise, economically, it makes sense. So they are all the same. So we're looking at a setting where everything is symmetric. And the Q is easy. So we want a simple model. So Q is one number, things are easy. So now let's go to the recruitment stage. Okay, so given the bidding behavior on the auction stage, beta FBA, given an expected participation level lambda, we can calculate the seller's expected revenue as R of lambda. And naturally, R of lambda is increasing. That's a direct implication of the property we just observed. R of 0 is 0, and R of lambda goes to 1 as lambda becomes large. So I assume V is between 0 and 1. R is increasing because first we have a higher chance of a higher value bidder who bids higher because beta is increasing in V, and second, beta is increasing in N, so they have higher competition. So there are two reasons for the seller to increase lambda. Okay, so if the seller chooses a targeted participation level lambda, with a recruitment effort X equal to lambda over Q, then the profit of the seller is R of lambda minus lambda times S over Q, where S over Q is the cost per participating bidder, right? If Q is smaller, then the cost per participating bidder is higher. Okay. So S of Q is like an equilibrium cost because it depends on the equilibrium action Q of the bidders, right? So if you have an interior equilibrium, it must be the case that marginal revenue is equal to marginal cost. So R prime of lambda is equal to S over Q. So that's good. The bad thing is that the profit is not concave, so we'll have corner solutions. So the first order condition is not sufficient. So we can have corner solutions. If you don't have a corner solution, we'll have an interior solution where marginal revenue is equal to marginal cost. So basically, if the equilibrium cost of a bidder is higher than the break-even cost S max, then optimal participation from the viewpoint of the seller is 0. If S over Q is smaller than the break-even cost, optimal participation level lambda S is going to be larger than some minimal scale, which is strictly larger than 0. And at this optimal participation level, we'll have marginal revenue equal marginal cost. So here's the picture from intermediate micro, if you like. So in blue, you have the marginal revenue curve, first increasing, then decreasing. So it's not a concave objective function. And in red, we have the average revenue curve. And you see, the average revenue curve is maximal where marginal revenue hits it. So from this picture, you can see that with a uniform distribution of values, the break-even cost of the seller is at about 0.14. So if the costs are above 0.14, the seller will choose the corner solution and produce nothing, even if. And if the costs are below 0.04, right, then the seller will choose the larger intersection, which is above the minimal scale, which is above about 2.6. Okay. Good. So that's it for the characterization. So we've calculated, we've solved the recruitment stage. Before this, we have solved the entry stage and the bidding stage. So now we can state the equilibrium. Equilibrium will be participation level lambda star, a belief about the participation lambda star, entry probability Q star, a bidding behavior beta star, and they have to be mutually optimal, and beliefs have to be correct on the path. Okay, so that's all standard. Is there a question?
I have one question, yes, and that is your choice of independent private values. It seems to me that a lot of the issues that you're wanting to confront are much more interesting in a common value framework.
I'm happy that you say
the
this.
Winner's curse.
Yes, exactly.
So I'm just wondering if you're going to talk about that.
Yeah, I will. Exactly. So for now, we'll have private values, but you're right that they're interesting things, and they're going to be interesting things with common values. Thank you. Good. So for now, basic model.
Sorry, Stefan. Yes? Nora had a question, I think.
Okay.
Yeah, this goes a bit back to what I think Ada asked before. Yeah. But I mean, because you said the Poisson is not without the Poisson doesn't, and it doesn't make a big difference if I know how many bidders are there or if there's uncertainty. But I mean, the game will be quite different, right? If the seller could commit on saying, look, I only ask 5 people or so, right? Then it would be a very different game from this mechanism design point.
Yeah. So it's it's sort of the critical point here is that the seller cannot commit to an X or announce X. Okay, and we'll see what is sort of the implication of that. Okay, great. So let's now look at some simple implications of this. So we'll just play around with this simple base model here. Okay, so first direct result, which we don't have to prove because we've already proved it basically, is the following. If lambda B max is smaller than lambda S min, meaning the bidder's break-even level is below the seller's minimal scale, then there's going to be no trade in any equilibrium for any S. So in the uniform example, if the entry costs of the bidders are 0.15, then we said that lambda B max is at about 2. The seller's minimal scale is at about 2.6, which is larger. And so this means there's going to be no trade for any level of S. So even if recruiting bidders is costless, there will be no trade. So what's going on here? Well, the seller would like to commit and tell the bidders, you know, I'm not going to recruit more than lambda V max bidders. If the bidders would believe this, they would be happy to enter. However, lambda is unobserved. And so the seller would have an incentive to deviate, and he will always deviate to a lambda that is larger than lambda S min, and which is larger than lambda V max. And then the bidders would not be able to recover their entry costs. Okay? So here the insight is that the lack of the commitment by the seller, not being able to commit to a particular lambda, together with the costly entry by the bidders, leads to excessive recruitment. The seller will have an incentive to recruit too many bidders, and this then precludes trade, even if recruitment is cheap, meaning even if S is small. Okay? So this is the implication of no commitment. It's a direct implication. I don't have to prove anything else, right? I think it's not neat. Notice maybe one thing. So how does the equilibrium now look like? So we have no equilibrium with trade. So how does the equilibrium without trade looks like? Well, it can't be that Q is equal to 0. If Q is equal to 0, that means no bidder enters. Well, if I know that no other bidder enters, I want to enter for sure. So that then the seller would have an incentive to recruit bidders if S is small. If Q is equal to 1, then the seller also has an incentive to enter. So Q has to be between 0 and 1. So the belief of the bidders has to be such that their expected utility from entry is equal to C. And then they will be mixed, and we'll have to set Q so that the seller doesn't recruit. Okay, that's the basic idea. Maybe to give you a little bit of idea of how things work here. Okay, so this is the case in which lambda V max is smaller than lambda S min. This happens if the entry costs C are too large. So now if you make entry cost C smaller, lambda V max will be above lambda S min, so we can have trade. So let's look at how this equilibrium looks like. Again, it's going to be intuitive how it looks like. And let me show you. Okay, so if lambda V max is larger than lambda S min, then there's going to be a cutoff such that the maximal equilibrium with maximal trade looks as follows. If S is above S max, then, you know, if the sampling costs are too large, the seller will optimally choose to recruit no one. Lambda star is equal to 0. That's obvious. For some intermediate region between the cutoff S hat and S max, the seller will choose a lambda star that is strictly positive above the minimal scale, at which marginal revenue R prime at lambda star is equal to S, and all the bidders who are contacted are happily entering. They're happily entering because lambda star is below lambda V max. However, as S decreases, so it becomes cheaper and cheaper for the seller to recruit bidders, the seller will recruit more and more. So lambda star will increase further and further until it hits lambda V max. At this point, lambda star can't increase anymore. So lambda star for S smaller than S hat will be fixed at lambda V max. And the bidders now become cautious to enter. Q star is between 0 and 1. And Q star is such that the marginal cost of an additional bidder S over Q star is exactly equal to R prime. Okay, so this is the bidder's free entry condition pins down the participation level in equilibrium. Okay, so in a picture, so here again in blue we have the marginal revenue curve, in red we have the average revenue curve. The minimal scale was at 2.6, and now suppose that the entry costs are 0.03. In this case, lambda V max, the bidder's break-even level is 5. Here, 5. So how does the equilibrium look like? Well, if S is above 0.14, there will be no trade. If S is between 0.14 and 0.06 or so, the seller will choose some number here, lambda, at which the marginal revenue hits the cost. Then as S decreases, the seller chooses more and more bidders until we hit 5, and then we'll enter the territory where the bidders start mixing and they become cautious to enter. Okay, so at this point, as S becomes smaller, it becomes cheaper to contact bidders. It's still sort of the cost of actually recruiting bidders will stay constant. They will stay at S over Q star equal to R prime equal to lambda V max. Okay, good. So observations, maybe here, there's excessive recruitment. So there is some trade, but there's still excessive recruitment. In what sense? Well, if S is below the cutoff S hat, lambda star is fixed at lambda V max. So independent of what the sampling costs is, even if it becomes very cheap for the seller to recruit bidders, lambda star is fixed at the bidder's break-even level, and Q star will solve sort of this equilibrium condition S over Q star equal to R prime. And the implication is here that the total recruitment costs are going to be a constant. So for S below S hat, the total recruitment cost lambda star times S over Q star is fixed at, well, lambda star is fixed at lambda B max, S over Q star is fixed at R prime. So the total recruitment cost, lambda star times S over Q star, sort of how much effort the seller has to spend in total, is fixed and independent of how costly it is to get bidders. So if it becomes cheaper to contact bidders, you know, the bidders just become more and more cautious, and so it's just harder and harder to motivate in proportion. So cheaper recruitment does not actually lower the recruitment cost. So if you like, sort of the physical friction of contacting bidders, the physical friction S is independent of what sort of the equilibrium friction is. The equilibrium friction is fixed. And there's an inefficiency as S is small, these recruitment costs are a waste. Why? Well, the seller would like to prefer to commit to lambda B max. The seller would like to say, you know, I'm never going to recruit more than lambda B max bidders. I'm never going to recruit more than 5 bidders. And if you could do so, then both the seller and the buyers would maybe be better off. Okay? And we would even get approximate efficiency. Notice one thing that is important now for later, for the sort of more subtle effect, if you like, is that the total recruitment costs here are proportional to the marginal revenue at lambda B max. Okay, so the larger is the incentive of the seller to recruit bidders, the larger is the total recruitment cost. Okay? And you know this logic. So what this means is if there is an auction that is able to squeeze out more revenue on the margin, that's actually a bad thing for the seller when S is small. And that we'll see this in a second. Okay, so questions about the result per se, and then we'll discuss sort of variations and extensions.
So one question which you may get to in your extension is the cost of participating. In practice, this issue that you're talking about is addressed to some extent by the participants adjusting their participation cost. So for example, if I think it's unlike I'm bidding on a contract to do for some work, and if I think it's unlikely that I will be a winner, then I invest very little effort and I just put in a super high bid for the project.
Yeah. So here we don't allow bidders to submit bids without investing the cost C. I think what you're suggesting is some sort of, you can invest more and more to learn more and more, and maybe this could even be, you know, productive. So that would be an interesting extension. Other questions, or should I go on? So let me go on. Okay, robustness. So first, this is the first price auction with a known number of participants, and we understand this is revenue equivalent to all standard other auction formats, English auction, Dutch auction, and so on. I like the first price auction because it's very natural. I take the best offer that seems to reflect how many markets work. Okay, so more generally, all the results that I've shown you, which are all relatively simple, do depend not on the actual auction format and, you know, solving exactly for what beta FBA is. They only depend on the shape of R of lambda and U of lambda. They depend on the shape of the revenue and the utility. Okay, so in a sense, they depend on how the surplus is split between the buyer and the seller and how the surplus depends on lambda. That's what's important. Okay, so in principle, we can think about sort of a more reduced form modeling of the bargaining here as well. And we can say if the R and U function have these properties, then we have these results. And if not, then not. Okay. Then we had homogeneous bidders. So this made it easy because we can, you know, everything is pinned down by free entry. It gives rise to this little queue. We can also think about ex-ante heterogeneous bidders who have heterogeneous entry costs or value estimates and then update their value at some costs. The advantage of that would be we get a pure equilibrium. So bidders enter when their entry cost is low or the value estimate is high. You could also think about a binary estimate maybe, and then only bidders and only those bidders enter with positive value estimate. The point here is the results will be somewhat similar in structure and we have somewhat similar qualitative results. Good. So variations. What I promised. Okay, so I have another 15 minutes. Is this right?
Yeah. I mean, you can go until 5 with the talk, including clarification questions. And if there is some time left for discussion, this is great. But we can also discuss a little bit after 5 if you have the time.
Oh, fine. So, but 15 minutes should be good.
Okay, great.
Okay, so variation number 1, uncertain seller type. So in the so suppose there is uncertainty by the bidders on what are actually the incentives of the seller to recruit bidders. So before in the equilibrium, the sellers, before in equilibrium, the bidders don't observe X, but they can infer X because they know, they have the correct equilibrium conjecture. Now, here is a variation in which the sellers are uncertain. So the way we model this is by saying, suppose there's uncertain cost of recruiting bidders. So the cost of recruiting bidders could be low, SL, or high, SH. And it's natural that a seller who has higher recruitment costs samples fewer bidders than someone who has lower recruitment costs. Okay, so SL samples more aggressively than SH. So I'm not sure as a bidder when I'm contacted, how many other bidders have been contacted as well. I'm not sure about the recruitment effort of the seller. However, I infer something from the fact that I've been contacted. Why? Because if I'm contacted, well, it's much more likely that the seller is a seller with low costs, because a low cost seller contacts more bidders than a high cost seller. So there's a sampling bias. Conditional on being sampled, I think it's more likely that it's the low cost bidder seller. So what this means is that, for example, if SL is very low, such a seller would recruit many bidders. So the bidders would be very cautious to enter. And if the bidders are very cautious to enter, actually the type who has a high sampling cost may not be able to recover his or her sampling cost and may be driven out of the market. Okay. So SH may be able to trade and be happy, but now there is this SL type, and now the bidders are uncertain which of these two types is it, and they think it's probably the low type, so I should be very cautious to enter. If the bidders are so cautious to enter, it's not worthwhile for the high type anymore. So there's an externality between these two going via the sampling bias. So this is for binary solicitation costs. So we can also look at a continuous distribution of recruitment costs. So suppose the seller solicitation cost S is drawn from a smooth distribution. Say S is uniformly distributed between 0 and S max. Sellers who have costs above S max will not be able to recruit any bidders anyway in the equilibrium. Okay, so suppose the costs are between 0 and S max, and suppose they're uniformly distributed, and we're asking what is the equilibrium like? Well, so here's the answer. There's going to be a cutoff of the entry costs of the bidders, such that if the bidder's entry costs are low enough, then every bidder will enter with probability 1. And given that every bidder enters with probability 1, all the sellers will choose a strictly positive recruitment level, lambda star as strictly larger than 0, at which marginal benefits is equal to marginal cost. So if C is below C hat, there's actually no impact of this uncertainty. As if C is larger than C hat, however, the market will unravel and Q star is equal to 0. So no bidder would participate. Bidders participate with probability 0, and all sellers will choose a participation level of 0. So no bidder recruits anyone except possibly the 0 type. You can see there are some technical issues. Okay, so this is a sort of a dramatic unraveling result. The basic idea is, suppose there would be an interior cutoff for the seller's sampling costs, so only sellers with costs below the sampling costs enter. Then the bidders update, they think, well, it's likely that the seller who recruited me is a seller who has even lower sampling costs. This drives out the marginal seller, and this whole thing unravels to 0. Okay? That's the type of result. So it just illustrates sort of this externality that we've also seen with the binary type. Okay? So that's variation number 1. Now let's go to variation number 2, which was immediately asked. Okay, so in many of the scenarios that I've shown you, actually there may be uncertainty about how many other bidders there are. So when I'm buying a house, the seller may say, there's this other bidder, there are lots of other bidders, actually, you better behave competitively. At the stage where, I've already looked at it, I've already invested all the time discussing with my family, then they will say, you better submit a competitive bid. And it's not so obvious that I should believe the seller, whether, how many other bidders there are. So in this scenario, the bidders do not observe the actual participation. And the bidders' bidding behavior now depends on their beliefs about the participation and not on the actual participation level. So this implies now a new consideration. Why? Because the seller now has a lower recruitment incentive. By recruiting more bidders, the seller is no longer able to affect the bidding behavior. The bidding behavior is independent of my actual sampling. Okay? So the seller will now actually have an incentive to cut secretly the recruitment. The seller has an incentive to say, I've recruited many bidders at the time, the bidders are participating, but then really recruit only few bidders because the seller cannot affect their bidding behavior anymore. And that has a few implications. So first, when there is trade and S is small, this is actually good for the seller. Not to have strong incentives to recruit bidders is a good thing. Why? Because we've seen that this implies lower total recruitment costs. So auctions that extract less margin surplus are good for the seller, for S being small. For intermediate levels of solicitation costs, it's actually a bad thing. So what's not going to happen is this incentive of the seller to secretly cut participation can lead to unraveling, and we have a unique no trade outcome. So if we start with the optimal participation level for the case with observable participation, we now make participation unobservable. The seller has an incentive to cut recruitment. Given that the seller has cut recruitment, the bidders will behave less competitively, and this will turn out to imply that the seller has even less incentives to recruit bidders, and this will all unravel down to zero. And last, there's going to be a robust no-trade equilibrium. There's always a robust no-trade equilibrium in which the seller is sort of caught in this bad expectation that the bidders expect the seller to recruit no one, and if someone is recruited, then only by accident. And if they're recruited by accident, they know there's no one else, so they bid zero. So the bidders expect no competition. They bid very uncompetitively, and so recruitment is unprofitable from the viewpoint of the seller. Okay, so this is what's happening. So the problem here is the seller cannot credibly commit to generate sufficient competition. So the problem with unobserved participation is this incentive to secretly cut participation.
So
notice now,
so it seems like this is very dependent upon the first price sealed bid format. So what's commonly done, for example, in home sales is where we could have unobservable participation is there's an escalation clause. So in the event that there's competition, I can put in, I can have my bid raised in response, which essentially makes it an ascending auction. And then I think you get around this problem.
That's interesting. And you probably have to have sort of laws that prohibit you to make up the presence of another bidder.
Well, there's some observability because it's all controlled by the agents, and so the agents have norms of behavior, and I think there's enough transparency between in this repeated game where the agents participate regularly.
Right. So two statements. So here, if you see, so with commitment, we have revenue equivalence, of course. Even if N is unobservable, it doesn't matter whether I observe how many other bidders there are. If the seller can commit to a lambda, and then I don't observe the realized little n, it doesn't matter whether we have first price, second price, ascending auction. But without commitment, we have these problems, and first price auction, second price auction, or ascending price auction are no longer revenue equivalent. And so the considerations that you're describing, they kick in, right? By the way, so in art auctions, there's what's called a chandelier bid. The chandelier bid is sort of the auctioneer just looks at the ceiling of the auction house and just invents a bid. Okay, and there's a lot of legal discussion whether that's okay or not. Okay, so this, and you can see how this could be a good or a bad thing, actually. So the ability to make up bids can be a bad thing for the seller, because you can no longer credibly convey the notion that there is another bidder, and then you may want to use agents, as Peter said. Great. So this is interesting, I think. So we'll study it, and there are some, interesting implications if the number of bidders is not observable, or if the seller cannot credibly commit to disclose it truthfully, and then maybe rely on some agents. Okay, variation number 3. So Peter suggested that quality uncertainty. So in many of the settings, so think about someone applying for a loan at banks, but even selling an asset as a company or selling a house, there will be some common value components or interdependent values. So let's think about that and what this means for this type of setting. So suppose there's uncertainty about the quality of the seller's object. Could either be a high quality or low quality object. And let's look at the extreme case where the bidders have pure common values. So the value is either V8 for all bidders, or it's VL for all bidders if it's a low value auction. Okay, so it's a pure common value auction. And as in a standard pure common value auction, let's assume that the bidders observe noisy conditional IID signals about the quality. So higher signals may indicate a higher probability that the quality is high. So, so the basic insight about common value auction is that there's a winner's curse. So winning is bad news about the value because everyone else has a lower signal. So what's important here is now the observation that if the more bidders participate, then there's going to be a stronger winner's curse. So if I don't observe how many other bidders there are, but I expect many other bidders to be participating, then winning is worse news if I expect more other bidders to participate. And so the more other bidders I expect to participate, the lower will be my bid because of the winner's curse. It turns out that has very similar implications. So in equilibrium, we'll have excessive recruitment, even if the pure entry costs are zero. And again, total recruitment costs in a variation with common values will be constant in the search costs of the seller. So as the search costs become smaller, what's going to happen is the seller will recruit more and more bidders. The bidders anticipate that there are more other bidders, okay? And because they anticipate there are more other bidders, they get increasingly cautious and submit less and less aggressive bids. Okay, and these two effects will just cancel each other. Okay, so there's a similarity between a common value auction in which bidders are concerned about the number of other bidders because of the winner's curse, and the entry problem where the bidders are concerned about the presence of other bidders because they're concerned about being able to recoup their entry costs or their information acquisition costs. And so on. There are some caveats. So these are auctions in which I'm uncertain about how many other bidders are present. And it turns out that many of the standard insights that we have into common value auctions only hold if I know exactly how many other bidders there are. If there's uncertainty about the number of other bidders, many of the standard predictions for common value auctions do not hold anymore. So if bidders are competing against an uncertain number of competitors, some new interesting effects occur, and that's a different thing. Okay, that's a caveat, so we have to be a little bit careful. Good, so I'm pretty much done. I think almost on time, so briefly maybe the literature. So there is a literature, of course, on auctions with costly entries. Some of you have contributed to that. So a lot of this literature has looked at sort of optimal auction design with commitment, finding that the seller can extract the full surplus in the most basic setting and runs an efficient auction. There's some work by myself and Asher on common value auctions in which the seller is informed. In that setting, the seller's recruitment strategy depends on the seller's private information, and being recruited contains information about the value of the object. And that introduces what we call a solicitation curse, and that may soften price competition and inhibit price discovery. So these are different papers of us, but they look at settings where the seller is informed about the private value, about the true value of the object. And last, there's sort of a literature on simultaneous search, which I like a lot. So there are two types of search models. One is I strictly search in sequence. So I contact bank number one, I get an offer from bank number one. After I've studied it and I don't like it, I go to bank number two. Okay. So then there's sort of strict simultaneous search, which is I contact 5 banks for a price quote, and then I take the best price quote. That's called simultaneous search. And that was studied, for example, by Burdett and Judd, was one of the first sort of attempts to also circumvent the diamond paradox, where the searcher chooses a fixed sample of prices. And you can see how this is sort of the same basic model structure that we have here. So basically what we're doing is we're studying a model of simultaneous search in which we add asymmetric information. There's private information about the values from the buyer side and price quoting costs. So it's not for free to quote a price. So I was trying to get a home repair, and it's actually not so easy to get lots and lots of price quotes. People are reluctant to come to my house and make me a price quote. Okay, there are costs of quoting prices, and there's also which. Okay, so this is simultaneous search, and basically what we're doing here is sort of we are bridging auction theory and search theory. Okay, so that's also the title was Auctions with Frictions. Good, so we're done. So here we go. So we studied a standard auction model. There's a seller, there's the number of bidders, but the number of bidders is not exogenously given. We want to study sort of informal market scenarios, and there we think that the number of bidders is jointly determined by the seller's recruitment effort, marketing, search, sale, and the bidder's costly entry decision. Not every bidder who's contacted will want to participate. there's a tension between the seller's desire to induce aggressive bidders. I want to have as many bidders as possible, and participation. If the bidders anticipate a lot of participation, they will be, difficult to motivate. There's inefficiencies. So first, there's wasteful recruitment, even if the recruitment is cheap. We've seen this. And there may be an inefficiency in the terms of the allocation of the object. There may be a market breakdown. And then we've studied a few variations. So first variation was there's uncertainty by the bidders about how many other bidders are contacted because of the seller's uncertain costs of sampling bidders. And there, the sampling bias introduces negative externality. If I'm sampled, I think probably many other people have been sampled as well. Second variation was unobserved participation. We talked about this. So I don't actually know how many other bidders I'm competing against. There's now this additional incentive of the seller to secretly reduce recruitment. And this lower recruitment incentive can reduce the waste, but it can also lead to too little competition and unraveling again. And last variation we looked at was a variation with quality uncertainty, where we have excessive caution, where because of the winner's curse, and this winner's curse has similar implication to the entry costs that we've seen before. So that's it. Thank you very much so far for your comments. This was great and a lot of fun.
Yeah, thanks a lot, Stephan, for the talk and encouraging questions. Are there any questions or comments?
Yeah, Stephan, I would have two comments actually. The one is, one could imagine that if it's a kind of eating up time or so to recruit many people, one could imagine that this also means you lose some bidders over time again. I'm wondering if that could be interesting. And the other thing is, we talked about that earlier. So I also have this paper in JET on where you can recruit more bidders for your auction, and there it turns out to help often that you say there's one person, one bidder who wins, or there's one who's there for sure. And I was wondering for your setup, if you think about a procurement auction, for example, and say it's automotive also, very often it's like there's one bidder who's like the default, so he's going to get the contract. Say he's on Schwäbische Alb, but you would like to induce some competition and maybe negotiate that guy down, right? But there's a kind of default, so it will not break down completely. I was wondering if that could, from a mechanism design perspective, cure some of the problems that you identify.
So a little seed of competition, you're saying, something like that. Yeah, no, that would be interesting. Actually, we have something because we need a refinement. And the refinement we're using is that the seller has to recruit a certain number of bidders, but we'll call it epsilon. So this is we make it small. What you're saying is maybe it's interesting to look at a large epsilon, not just as a refinement, but actually say, suppose the seller has to recruit a certain number of bidders. So this is a little bit of competition, of commitment. The seller has a little bit of commitment, and maybe this helps already. So yeah, that could be very interesting. Thanks.
I also have two comments or questions. So first of all, I mean, like, this is super interesting. I found this surprising, and obviously it's also important. It seems that this lack of commitment is crucial. So I was wondering whether you considered cases in between. So for example, I could think of this as, well, when I choose X, there's also going to be a signal that is observed by all potential participants about this X. And now in your case, you basically have no precision at all about this. In the perfect commitment case, you would have like infinite precision. You could consider cases in between, I guess.
Yeah, we could have some sort of noisy public signals, right?
Yeah. So yeah, because that also seems to reflect sometimes what's going on. I mean,
so one way to think about the axis, this is say you have a banner on the highway, and you choose how long to have this banner up on the highway. And the longer you have the banner up, then the more people will drive by and see it. So people are driving by at some Poisson rate. The longer you have it, the more people see it. So this gives rise to a Poisson distributed number of bidders. But then you could you could have it for multiple days, and people drive back and forth, and that's your sort of public signal. I think that's very good.
Yeah. And then the second question or comment would be, like, it seems that there might be potentially interesting interactions with like reservation prices, like that are unknown.
Yeah. Yes.
That you also have like potentially a lack of commitment that, well, I guess similar problems arise. Plus, yeah, like if you don't know how many people show up, you might also have interactions there.
Mm-hmm. So I didn't mention this, but we have something about the reserve prices. Mm-hmm.
Okay, cool. Yeah, that's great paper.
I have a question regarding the variation of the model.
Mm-hmm.
So instead of extension, I've been wondering, have you thought about simplification? Specifically, have you thought what happens if the bidders are symmetric? Instead of having different valuations, you have the same valuation?
Yes, we thought about that.
Do the results hold through, or?
Yeah, I think so. The question is which results go through. So some will go through. I'm hard pressed now to give sort of which results go through and which not. But sort of the basic idea is you can see that some of the results really don't, the distribution of the values don't matter too much.
Mm-hmm.
I guess you would get stronger results with unobservable participation, right? Because then you don't have this incentive to all the incentives with unobservable participation is to get a higher V. If this incentive is gone, and then the only incentive with multiple bidders is to get the bidders to actually submit aggressive bids in a sense. If you, in particular, if you get one bidder for free. So you maybe get even stronger results. Very good. Yes. Thank you.
Sure. Thank you.
If I could add one more question, and that is the marketing costs that you have here. One could think of them as actually being productive to the buyers. So, for example, my marketing is to present a clearer description of what I'm selling, and that thereby reducing the buyer's participation costs. And we see that's this sort of thing all the time.
Yeah, so one could think about sort of paying a subsidy to the bidders or making S smaller, but making S, so you can think about the internet, and the internet does two things. It makes it easier to contact bidders, but that may actually not be the important part. The important part may be that when I post something on Immobilien Scout, it actually makes it easier for the bidders to evaluate the house. So maybe it reduces the little C here, the entry cost. And I think that may be more important. So thinking about this, sort of what is the important part of the internet? Maybe it's not the reduction of the S, but it's really the reduction of the C. I think that's how I understand it, right? The seller could sort of make it easier for the bidders to evaluate. So this is lowering the C. And that could be sort of more important than lowering S.
Correct. Yeah. And of course, that's even more important if you're in a common value setting.
I see. So yeah, so it's a linkage principle. Very good.
Since we are at the end of our official time, let me just quickly announce that this is the last talk of this year, and we will be back after a winter break on January 18th. And our program for next term is finalized, so you can check it on our website. But yeah, I guess we have time for one or two other questions. Okay, if there aren't any, then perfect. We are exactly in time. And Stephan, thanks a lot for
I thank
your talk.
You and everyone else. This was a lot of fun. I wrote down a lot of questions and suggestions. So thank you very, very much. It was a lot of fun. Thank you.
Yeah, thanks to all participants, and we wish you happy holidays. See you in January, hopefully.